Since the only agent is the gravitational force which acts on the black hole, you can equate the magnitude of the gravitational force to the F-net magnitude and find the mass of the black hole. The distance r is known because we know the position vector of the star, through which it is possible to find the r vector. So this is the gravitational equation. I just rearranged the terms, and using this equation it is possible to find what is the mass of the black hole. And what I have done is that I have calculated the black hole mass at all the given samples, and I noted that the mass of the black hole is more or less the same at all points, and I have found the average mass of the black hole. Now let's take a look at the code. So here I have set the mass of the star to be as 1.88 times 30, and the delta t is going to be 1d. And I will highlight the obvious differences what I made. So I would like to store the output in a file so that later I can open and do some analysis. That's the reason I'm using a data writer. And this is where I added some logic to find the average mass of the black hole. And we find the initial velocity, the final velocity, through which we find the momentum, initial and final. We find the delta v, delta p, and we find the dp by dt. And using the equations, we can equate f net to be dp by dt. This is a vector, and here is where we find the p hat, and p hat would be in the direction of the initial momentum for that particular point. And here we evaluate the d magnitude of p by dt, and this will be nothing but the parallel component. So this is going to be a scalar, and this is a vector. So here we get a vector over here, and now we know what is the parallel component of the force, the F net, and by vector subtraction, if you subtract dp by dt, if you subtract the dp by dt parallel from dp dt, we'll be getting the perpendicular component, and here we'll be getting the F net perpendicular. Here is where I find out what is r vector. I find the unit vector r hat. This is just for my debugging, and this is the g, and the mass of the black hole is the same equation what I put in my slide. And here we take some arrow scale to plot the vectors, and here I sum up the mass of the black hole for the different points, and finally I'll be like coming up with the and over here you can notice that once I know the sum of the mass of the black hole at all points, and I know the total number of samples, here is where I print the average. So let me give this a run. Yeah. So the blue what you're seeing is nothing but the F net perpendicular, the black one is the F net parallel, and the yellow one is the F net, which is the net force acting. So whenever the black arrow is going to increase in the side, or the right hand side in this case is nothing but in line with the direction of the motion, you can notice that the velocity of the star is going to increase, and when the black arrow is like almost nothing or it is zero, the velocity is going to be constant. Now let's try to address the what if case. If the mass of the black hole is going to go to 2 times, the F net is going to increase to 2 times. This means that the F net parallel and perpendicular, they are also need to increase. But let's assume that provided if F net perpendicular is same as F net perpendicular, when the mass of the black hole is 1 time, the path which the star is going to take is going to be the same, because the F net perpendicular is a component that is going to decide the curvature. However, it cannot happen. That means F net parallel must increase to compensate or to give the net F net. If F net, however, if F net parallel is going to increase, it's going to like increase the momentum of the star. That means it's going to increase the velocity of the star, and the star is going to orbit the black hole faster. So what I would expect is that I would expect the star that orbits the black hole to approximately take only half the time what it has taken previously. Thank you for listening.